All right, welcome everybody. Today we're going to talk about lesson number 93. This is section 12.3, the tangent line problem, day 1. Notice I kind of bolded and underlined the title there. The idea of the tangent line problem is one of the biggest and most important problems that you'll ever solve in terms of calculus, so it is a relatively famous thing. Notice that there in homework 93, there are only 5 problems, definitely focusing on quality over quantity. Just make sure you read the directions carefully. Some of them are going to ask you to do the tangent line problem at a specific point, and some of those are going to ask you to use the general form. You'll know much more about what that actually means once we get through the lesson, but again, please just make sure you read the directions carefully. So first, a lot of people, when they get to calculus, they ask themselves, what is calculus? The truth is that calculus is the study of rates of change of functions. First, you're going to study how different things change in relation to each other, usually x and y. And then you're going to talk about, after a change occurs, how much is left or how much is accumulated. So in case it comes up at a party this weekend, what is calculus? It's a study of the rate of change. Everybody knows slope. You've been talking about slope for a long, long time. And basically, you've only really dealt with it in terms of lines. And of course, the slope of a line indicates the rate of change, rise over run, change in y over change in x, y2 minus y1, x2 minus x1, that relationship, that fraction. So you've been talking about slope for a long, long time. What we're going to talk about now is what if you have something other than a line, how much you calculate that rate of change. So consider here, we have obviously a downward facing parabola. And let's say you were trying to find the slope at some potential specific point. If you were to calculate the slope here at the point x1, y1, compared to the slope of that same quadratic here at the point x2, y2, you would hopefully be able to realize visually that the graph, the slope, is rising more quickly here than it is here. Obviously, both of those have positive slopes because the line is rising, but you can tell that because it's steeper here at x1, y1, that it's rising more quickly than it would be here at x2, y2. Here at the point x3, y3, because you have a horizontal line, because you're at the maximum of this quadratic, you would say that the rate of change is 0. And then let's say you were to try to find the rate of change here at a point like x4, y4. Well, obviously that would have a negative slope because of the fact that the line is falling. So again, a big idea of what we're going to talk about here is rate of change of something other than just a line. So if you were trying to find the rate at which a graph rises or falls at a single point, what you are actually finding is the slope of the tangent line at that point. Remember, of course, back from your geometry days, that in order to be a tangent line, it means you intersect the graph exactly once. Here are just a couple of examples, again, of what you're talking about when you're trying to find the rate of change of a graph at a specific value. So here we have some kind of polynomial function. If we were to draw a tangent line at this specific point P, you see that the slope there, the slope of the tangent line, would obviously be some positive value. Whereas if we were to do it here on this graph, it would obviously be some negative value. And then again, we see a second situation where the slope of that tangent line would be 0. In the previous slide, it was because it was the maximum, and now, of course, it would be the minimum. Spoiler alert, the maximum and the minimum kind of wind up being the most important, but it is, of course, vital that you're able to consider all 3 cases. Just a little bit of a disclaimer down here. Usually when you did points of tangency back in geometry, you did it for circles, where once you intersected once at a point of tangency, it never intersected the graph again. For something like this first example, if you were to continue this tangent line, it would intersect the graph a second time. And basically, this little disclaimer is just letting you know that that's okay. You obviously are going to be asked to find the slope at a specific point, and that's the only one that you have to be concerned about. So the first thing that they kind of go over in this section is how you might visually approximate the slope of a graph. Truth is, something that you could already know how to do. You're basically looking at a graph. You would find a point, or I would give you that point rather, let's say in this case 1, 1, and then you would have the graph of x squared, which of course we all know looks like that upward facing quadratic. If you have the point 1, 1, and I asked you to just ballpark a tangent line, you would perhaps take a straight edge. You would kind of angle it so that it looked like it was appropriately hitting the graph exactly once, and you would get a line that looks like this. Obviously, it has a positive slope. Notice that it is relatively steep, which implies it should be a whole number as opposed to being a fraction. And if I was to ask you to estimate that, perhaps you would look at this and say, okay, the change in y is around 2, the change in x is around 1, so that tangent line approximately has a slope of 2. Again, something that you should already know how to do, but something that's not really very useful. Obviously, anything that we just estimate or approximate isn't going to do us much good. So while it is a thing, and it's good that you know that it's a thing, in a couple slides from now, we're going to define a much more precise process. So in order to do that, in order to find the slope, we're of course going to use the limit process, which should hopefully not be a surprise given that this is a chapter on limits. So if you are trying to find a systematic approach for finding the tangent line, we're going to start by using the secant line. Hopefully you remember back from your geometry days or back from the beginning of the year, a secant line intersects a graph at 2 places. We're going to assume that one of those points is the point of tangency, and then we're going to select some second point on the graph. So we are going to call that point of tangency the point x, comma, f of x. And again, the f of x just stands for a y value, but we're going to call that f of x. That f of x will change for every problem depending on what the function is. Then, because we're trying to study rates of change, we have to pick a second point that is some distance away from our original point, x f of x. So we are going to consider a second point, which is h units away. So h units away from x is x plus h. Then, in the same way for this first point, if you knew the x value, you would plug it into the function and get the f of x value. If you know the x plus h value, you would plug it into the function to get the f of x plus h value. So if you were talking about those 2 points there, then you are talking about the slope of the secant line being equal to y2 minus y1 over x2 minus x1. And of course, if you look at your 2 ordered pairs, here's your y2, f of x plus h. Here's your y1, f of x. That's how we get the numerator. Then you would do y2, which is x plus h, minus y1, which is x. And then, of course, the x's would cancel, which is why you're simply left with an h in the denominator. So that looks familiar. That is obviously the difference quotient, which we have been doing now for a couple of days. What you need to realize is what that difference quotient actually represents in terms of the graph and in terms of the function is it is the slope of the secant line. You are going to abbreviate the slope of the secant line with msec, M for slope, and SEC to represent the secant line. The beauty of this procedure is as you get more accurate approximations, of the secant line, what you're actually doing is getting closer and closer to making it a tangent line. And what do we call that when we get closer and closer and closer to something? Well, that's a limit. So let's kind of look at what that means graphically. So again, here's that same picture from the previous slide. Consider any function f of x. Consider a point of tangency, x f of x. Consider some second point on the graph, h units away. Well, let's say that you were to take these 2 points, and let's say you were to move them slightly closer together here in the second graph. Let's say you were to move them even closer and closer together here in the third graph. And let's say you were to get them so close that they practically were on top of each other. That means they basically would become a single point. And of course, if you intersect a function at just one single point, that takes the secant line and turns it into a tangent line. So how is this happening? Well, because the values, the 2 points, are getting closer and closer together, that means the distance between them is getting smaller and smaller and smaller. Because the distance between them is h, getting smaller means it's going to 0. And again, as you're getting closer and closer to something, that is called a limit. And this limit process allows you to find the exact value of the tangent line, which is always 100 times better than just an estimation. So here is the definition of how you find the slope of a graph at a specific point. You are going to realize that it is equal to the slope of the tangent line at that point. That slope of the tangent line is called m. The way that you would calculate m, so again, the slope of the tangent line, is by taking the limit of the slope of the secant line, and the slope of the secant line is found by using the difference quotient. So technically all the things I'm going to show you from this slide forward, you already know the mechanics of how to do, but now you just have to know when to do it, and you have to understand a little bit more about why you're doing it and what the value that you're finding actually represents. Excuse me. So here in example 3, they want you to find the slope of the graph, which again, that's always code for slope of the tangent line, at the specific function x squared, and they want you to do it at the specific point -2, 4. So this down here, denotes for you, denotes for you here the formula. So I put it here so that we could see it. I also have for you the graph of x squared and the point -2, 4. It also has the answer there, but it's kind of good to consider the graph in relation to these problems. If you were to get a slope, in this case looks like -4, and you were to draw it onto the function, you'd want to make sure that it makes sense. If you got an answer like +1/3, that is clearly not a slope of negative or positive or -1/3. So you kind of want to keep that in mind. So here's the thing. If you're trying to use this process, which we're going to, and you're trying to do it at a specific point, you have to use this formula, but you have to use it for a specific value, which in this case is x equals -2. Basically, for the remainder of this lesson, there are two types of problems: finding the slope at a specific point or finding a general slope. If you're ever finding it at a specific point, then instead of using x in the formula, you're going to actually use whatever the x is equal to, which in this case is -2. So taking the difference quotient, okay, which again is the slope of the secant line, msec for short, instead of finding f of x plus h, because this specific problem has an x of -2, then you're going to find f of -2 plus h. Minus, instead of f of x, you're going to do it specifically at f of -2. And then, of course, you're going to divide it by h. F of -2 plus h means go to the f function. Anywhere there's an x, put a -2 plus h. F of -2 means go to the f function. Anywhere there's an x, put a -2. So that means you're going to square and you're going to square. In order to do this calculation, of course, it's a FOIL. Then start canceling, cancel the 4s. Notice that in the next step, you're only left with terms that have h's, and spoiler alert, that should always be the case. Reduce an h, and you are left with -4 plus h, and again, the h cannot be equal to 0. That's kind of always a qualifier because the difference quotient wouldn't exist if that wasn't true. That -4 plus h, what that represents is the slope of the graph at that specific point. Okay, so the slope of at that specific point, in order to actually turn it into the slope of the tangent line, you have to go ahead and take the limit. So you're going to take the limit of the slope of the secant line, which means you're taking the limit of -4 plus h. And of course, if you put a 0 in for all the h's, you wind up getting a slope of exactly -4. And again, if you go back to the graph, and you look at that tangent line through that specific point, a slope of -4 really seems pretty reasonable. Right, so here in the next example, they're asking you to find the slope of the graph of x cubed at the point 2, 8. So again, I have a little picture for you. Just so you know, the point 2, 8, if they had only given you the value x equals 2, you would have to actually find the value of 8. And by doing that, you would, of course, just plug it in to the x cubed. If you take a look on the graph at the point 2, 8, if you were to try to just kind of eyeball that slope, hopefully you would agree that it has to be positive and it has to be relatively steep. So the answer that you get to this problem should be a pretty high positive number. So just something to keep in mind as you work here. Because they are asking you to find the slope at a specific point, you're not going to use the x plus h. You're going to use the given value of x, which is 2, in your slope formula, which again, I have for you there at the bottom. So you're going to go ahead and start. The formula for the slope of the secant line is equal to f of 2 plus h minus f of 2 all over h. And again, you're specifically using the value of 2 because they're asking you to do this at a specific value. When you go ahead and do the next step, you're going to go ahead and find f of 2 plus h. So if you're going to find f of 2 plus h, that means you're going to go to the f function. Everywhere there's an x, you're going to put a 2 plus h, which means you're going to have to cube it. Then minus f of 2 all over h. So you're going to have to be careful here with your 2 plus h cubed. So that is essentially 2 plus h times 2 plus h times 2 plus h. So I'm going to kind of pop out here for a second and do my work on the side. So 2 plus h times 2 plus h times 2 plus h. Remember, you would start by foiling any two of them. So I'm going to multiply and get 4 plus 4h plus h squared. Now you're going to have to multiply that trinomial times that binomial. So if I start by multiplying 2 times 4, 2 times 4h, and 2 times h squared, then I'm going to multiply everything by h. So that's 4h squared and then h cubed. If I go ahead and try to clean that up a touch, looks like I can rewrite this as h cubed and then 6h squared plus 12h plus 8. And let me just go ahead and make sure that I wrote that correctly. So 8 plus h cubed plus 12h plus h, 6h squared. Okay, that looks good. So as I go ahead and move back to my problem here, I'm going to go ahead and write my next line of work here as what I just found. So h cubed plus 6h squared plus 12h plus 8. And then I don't want to forget to subtract f of 2. So if I'm going to go ahead and subtract f of 2, so minus, what do you get when you plug 2 into x cubed? That would be 8. And then this is all going to be over h. So I'm going to go ahead and start reducing and canceling where possible so I can cancel out these 8s. And remember, when you're doing these problems, everything except the values that have h should in fact reduce. If you go ahead and look at what you're left with, so if you look at all these h values on the top and you look at this h value on the bottom, hopefully you would agree that you can reduce an h from everybody. So that's going to give you an h squared plus a 6h plus a 12. And then from here, you're going to want to go ahead and make sure you, again, put back in your limit statement. Technically, you should write it the whole time, but I understand why that's hard to do so. So remember that the slope of the secant line is going to be equal to the limit as h goes to 0 of h squared plus 6h plus 12. So if everywhere there's an h, you go ahead and plug in a 0, then each of these are going to cancel, and you're going to be left with a final answer of 12. And again, if you go back to what I had originally mentioned, you should be getting a relatively large positive slope. So I think 12 would fit the bill. Something else I just want to point out here, you probably remember, or you might remember from chapter 9, the binomial expansion theorem. Remember, this was supposed to be a shortcut for you to do the higher powers. If you were being asked to raise something to the 0 power, the first power, or the second power, it really just makes sense to go ahead and just do it outright. For something like the 4th power or the 5th power, it might make more sense to use the binomial expansion theorem. Here for the cube, it's kind of a toss-up. If you were going to use the binomial expansion theorem, you would have to use the idea that 2 plus h cubed means that x would be your 2 and h would be your y, and then you would have to go ahead and follow the pattern and use the coefficients. I don't know how much of a time saver that would actually be, but I do want you to realize that it is an option if that's something that you're interested in. Then the second type of problem that you're going to have to be able to do here is just where it says find the general slope. Notice they are not asking you to do it at a specific point. So if they are not asking you to do it at a specific point, you're going to leave x's as opposed to actually making them numbers. So f of x plus h means in the function, everywhere there's an x, put an x plus h. Minus f of x means subtract, don't forget parentheses, and subtract the entire original function. Multiply, distribute. Lots of good cancellation should happen. So all the x's, all the constants, reduce an h, and you're left with the limit as h goes to 0 of just -2. And obviously, the slope of a constant is simply that constant. To be honest, these problems are a little bit lame because if you're finding the slope of a line, yeah, it's obviously going to be the same m that it always is. I will caution you though, even if you think you know a shortcut, even if you think you start to see a pattern, you still have to do this process, okay? For the homework tonight, I'm only picking 5 problems because I'd rather you do all 5 problems really well and thoroughly as opposed to doing 20 problems halfway. I know I had to email a couple of you about not showing all your work, so don't be a step skipper. This stuff is too important. Just to kind of reiterate the point between the 2 different types of problems that we did in the last couple of slides and the 2 different kinds of problems you're going to see tonight. In both of these cases, you are finding the slope of the tangent line by finding the limit of the slope of the secant line. But for the first case, you're doing it at a specific point. So that was examples 3 and 4. For those types of problems, you're actually going to make the x whatever the x value of the ordered pair is, okay, whatever the constant is. The second type of problem is if you're just finding the general formula for slope, in which case you're going to leave them as x's. The process is very similar, but again, you do have to make sure that you're doing what I asked for when I ask for it. Kind of putting those 2 things together, okay? What if I gave you a function and I said find a formula? That means keep it general with x's. But then at the end, if I said, what is the slope at these 2 specific points, you would actually have to use those x values. So here, start by doing the general formula with the x's. So set up a difference quotient. Everywhere there's an x, put an x plus h, minus the entire function f of x. Do the FOIL and distribute. Cancel out all the x's, cancel out all the constants. And again, that should always happen. Reduce an h. Take the limit, that is going to give you that 2x is the slope of the tangent line, which is the slope at any point. If you specifically want to find the slope of the tangent line at -1, 2, you're going to take this specific x value and plug it in for x, giving you a slope of -2. I think you would agree that the slope of that line looks pretty -2-ish. Then if I said find the slope at 2, 5, you're going to take that specific x value, plug it in. That would give you a slope of 4. And again, if you were to consider that tangent line, I think it pretty clearly looks 4-ish. So again, I know that it kind of seems like we're doing the same thing for each problem, and we are, but you have to, again, make sure that you know the slight differences. So one final problem, and again, if you're feeling mathy, maybe you could pause and try it. If not, if you're able to kind of work through this problem with me, it really does go over everything you have to know for today. So starting with find the formula for the slope of this graph, that means you're going to leave it as x's. So starting off with the slope of the secant line is equal to f of x plus h minus f of x all over h. So f of x plus h is going to be x plus h squared minus 2 minus the entire f of x, which is x squared minus 2. I'm going to drop my h in the denominator just for a second. I'm going to FOIL x squared, 2xh plus h squared minus 2, distribute. Cancel the x's, always should happen. Cancel the 2's, always should happen. That is going to leave me with the limit as h goes to 0 of 2xh plus h squared over h. Just like always, an h should reduce, so that is going to give you the limit as h goes to 0 of 2x plus h. If you were trying to find the slope as the limit as h goes to 0, if you make h equal 0, you are going to get the slope of the tangent line equaling to just 2x. Okay, so 2x is the general slope. They wanted you to do this problem at -3, and they wanted you to do it at 1, -1. So after you have the general formula, if you then want to get specific, choose the specific x value. You'll have a slope of -6. Choose the specific x value. You'll have a slope of 2. And again, what was this problem? It was x squared minus 2, which means that it's a graph that looks something like this. If you were to choose negative 3 comma something, or negative 3 comma 7, and you were to find the slope of that tangent line, I think negative 6 is reasonable. If you were to choose the point 1, negative 1 and find that slope, I think positive 2 would be reasonable. So if the graph is not provided for you, it's never a bad thing to kind of make your own.